All right, so okay, this is lecture 16. Now we are going to stop talking about water. We are going to start talking about solid waste. Okay, it's nothing. Everything about water is over now. Today is more about solid waste. Next week is about air. The following about more topic related to climate change and energy. Okay. All right, so waste management. Before that, I want to just mention what is on the final, because that's the one important thing that you have to think now. Drinking water treatments, wastewater treatments are on the finals. These two constitute two long questions. Okay, one is a hardness question, another is a basically wastewater questions, which is mix of mass balance and all. And you already got the homework questions, and there are some tricky questions related to mass balance there, but those are explained in the office hour as well as the video from last year. So I put those links here, so you can check those mass balance for different location in wastewater treatment plants. Those are things you need to solve the question in homework. Homework 5 is due on Thanksgiving, before Thanksgiving. That's November 24th. I'll also release another homework on 24th. That's the last homework for this quarter. Those two homeworks will be part of the finals. So make sure that you don't, make sure to get this done early. Again, there are some mass balance. Yesterday I did all those in the office hour. So this is what I did in the office hour. So I post those things. These are the equation you may need to solve some of the questions. And these are mass balance equation for different location in wastewater treatment plants. So check those out before you ask questions on that. Again, last year video also I posted, YouTube video, which has explained those mass balance. All right, so today class is very much one class that, next year on the winter quarter, I teach a class called Sustainable Waste Management, that's CE154. And the prerequisite for that class is this class. Okay. So what we are going to cover in today and tomorrow is basically a condensed version of what you learn in that entire quarter. So it's a content, obviously it's not the everything, but you will get a sense of that. And that class is not as big size as this one. It's only 60 students. It used to be 40, but I increased because all the time there are over enrollment. So I ended up making it 60 from beginning. The reason class is very useful is the difference between this class and that class is writing. Okay, there is no finals. You write a report, you work with a team, you design a sustainable treatment system as a team of 5 or 7 students or even 8 students. You write a report, you learn how to write a report, and that's the report you can take to your employer. Next time you apply for interview, they always ask for writing. If you have writing samples, many undergrad students, at least some undergrad students, may have report writing experience, or they have published a paper as a co-author. They take that usually, but many of you will not get that chance, or at least it's not feasible. So this class provides you that. You can take this is a very realistic report. You'll talk about this project, what you did. So it's kind of a conversation starter for many of the interview questions. So this is very helpful. This is not the only class. It provides that opportunity. There is another class I teach. It's called Green Infrastructures in the spring quarter, that also give you the same ability. Okay, so that's the big difference. And the reason I say this one is this class is if you are not in civil engineering department, you have to ask me for PTE for early enrollments. Okay, so if you are in this class, send me email. If you want to enroll, I'll give you the PTE. But if you are in civil engineering students, you don't require any PTE. You can enroll directly. So I also posted the syllabus of that class on the CCLE so that you can see if this is something useful. Again, you are not required to take this class. If your interest is that, you can take it. Okay, so I'm not here advertising it because I want you guys to take it because you don't want it. Okay, you take only class that you find useful. something that you find relevant for your careers as well as interest. So that course details, we have a 3 weeks, the 10 weeks. The very first 5 weeks, we are going to learn about different technology that can treat hazardous waste. Then week 6 to 7, you learn about different technology that can actually treat municipal solid waste, which is not hazardous in big cities. And in the last 2 class, you learn about how to harvest energy out of those waste, how to harvest resource out of those waste. And again, you are going to write reports, which is we help you, or TA and I will help you every few weeks. So this is a periodic assignment. There are less homework there because of that reason. There is only 1 midterms. And basically after midterms, you are writing reports, not much homework. We are working together as realistic project we can think of. And that project choice is also yours. If you want to have a project that you are interested in, we can create that project for you. And so as you can see, this is the entire quarter of class. I can teach virtually in 2 classes. So I'm going to give you at least what the most important part of those class in these 2 classes. And you are going to also have the same homework or similar type of homework when you take that class. So you at least getting some 30% of the class concept in these 2 classes. Okay, so again, as I said, this class is very much about sustainability, because environment is one pillar of sustainability. Economics is the second pillar. Third is human well-being. Okay, so you have to account for all 3: economics, environments, and also people. So this class obviously address most of them except economics, because I don't really teach you the cost of environmental treatments. In that class, you'll learn the cost so that you know the which treatments is feasible, which treatment is not. For instance, if you know that we have lots of nuclear waste because we are creating nuclear weapons as well as for energy. The biggest reason, or the why people are opposed to nuclear waste or nuclear power plant, is the occasional accident that may happen, but the chance is very low. It's infinitely low compared to many things. It's a very well-proved technology. But also the other side is the waste that we have to deal with, and those waste will last for millions of years. So that's why there is a phobia for what we deal with that waste. So in that class, I asked this question, thought process. Imagine that you are a superhero, or imagine you have all the powers. Where you are going to take that waste to? So one student says, I'll be Superman. I will carry that entire waste into moon and dump it there. Okay, which is true. Now we have technology to dump that waste there, but do you know the cost of that? Okay, so the cost of taking 1 glass of water to moon is a lot, right? Because you are going against gravity. So that's the reason we have technology to solve every problem, but it costs money, and that is not feasible. So this is the class is all about learning that process. So as you can see over here, this is one example. Is when you are building a city like Los Angeles, you need resource. As your city grows, the resource become more and more expensive. For instance, cost of living in Los Angeles is high because there are too many people. There are too little space to live here. That's why buying a 2-bedroom apartment costs $1 million right near UCLA. And you can go somewhere else and buy a mansion with that, right? And so that's because of resource. We don't have enough resource. Land is okay, but something that you definitely need is water. Without water, civilization lost. If you think of most of the ancient civilizations, they are near the big rivers because that's what is a critical component of big cities. So traditionally, all the city management is related to the top process, where you see water and materials is extracted from surrounding areas from far away, and then used up and you dump it. Okay. For instance, Los Angeles, all the wastewater goes to Santa Monica rivers or not river, Santa Monica near the ocean. Okay. Everything dumped into ocean. Solid waste goes to landfill. There are many landfills near LA. In fact, whole LA city is a kind of a landfill because there are many sites which has been dumped with many things over years. Now they are trying to treat it. And there are many oil refinery in Culver City area and many other places. So as you can see, we are living with pollutions. In fact, LA was one of the city which has worst air quality, used to be, but now it has improved a lot. So that's because if you are not managing waste proper way. Whereas the future way of thinking is you take this waste, you use it up, but then you extract some more value out of the waste. For instance, wastewater. You learned that last class. Wastewater, 90% of the wastewater is actually water, 99%. So that's valuable in Los Angeles because you are paying so much money exporting them from far away in Colorado rivers, in Northern California, then you are just dumping it away. Okay, and we have technology to clean it up, drink all of them. In fact, if you think of what astronaut drinks in the space station, they drink their own they drink their own waste, right? So that's exactly how it goes. That means if you use reverse osmosis, you remove everything, you clean the water as clean as any water. So why are you not doing that one? The reason is also cost. Okay, if you can find a cheaper alternative, we are going to use it, even though it's wasteful. So the challenge of our future is about how to redesign this technology in a way that will cost less and less. And that's exactly what we are all striving to do. And I'll give a few examples. But historically, it's not the case. If you think of 1960s, catching river was very common. Catching river, the river catching fire was very common. This was a river that caught fire in 1960s in Ohio, Cleveland, Ohio, because municipal waste has been dumped into this river for a long time. Because there was no practice there for how to manage waste. And if you want to see a movie dramatizing everything that's happened real life, look at this movie, Civil Actions. The ending is not very good, but that's how the real life is. Okay, many of the waste are dumped into locations where common people pay the price. Corporates or big company, they can get away with that. And that has been the case in many places in capitalist society, which is positive and negative side of it. But it doesn't have to be that way. If we all understand how to manage waste, this issue will never happen. So that's why historically the remediation technology has been evolving in different ways. As you can see, initially it was mostly regulations. Ex situ means you take the waste and treat somewhere else. It becomes very expensive because the whole travel and everything will introduce more issues and more cost. Then they start thinking of in situ technology, means you treat right where it is generated. Okay, it's like imagine treating all the wastewater far away from Los Angeles. So much expensive. You treat right here where it is created. And then in situ technology was not very cheap because you are using so much chemical, using so much resource. So what they start doing is developing green method where it doesn't require that much chemicals, and it can treat itself by using nature-based method. That's the third revolution. And the fourth revolution, which is right now, is more about minimizing the waste altogether. Okay, and actually creating the resource out of it. So the green technology means you are using resource that is not harmful to chemicals, but you are still treating them. But the now new way of thinking waste is you don't treat waste as a waste. You treat waste as a resource. For instance, all your electronic waste used to be dumped into landfill. Now we think there are a lot of gold there, lots of rare earth element. Those are very valuable. That's why next time when you think of your laptop or your iPads or phone, Apple is asking you to recycle for free, but they are making money out of it. It's not recycle for free. It costs them more money if you don't recycle them, because extracting aluminum is more expensive than just using the pure aluminum that they use here. Okay, so that's the new way of thinking, how to recycle and extract resource out of it. And a few weeks ago, I was interviewed in Spectrum channel about how to manage electronic waste. I'll share that video, 2-minute video. on Campusware. You can check that. That's all about how to get those value out of your broken computers or electronic waste. So, so overall goal of this method is basically extract any resource you can get and get the resource out of it. So now all these things are possible because if we don't do it, you are breaking some laws. Without laws, nobody will do it. Everybody will dump their waste. If there is no law saying that you should put your waste not in the land in your dustbin, is I think of like a roommate situation. I had a roommate who was very much throwing stuff wherever he want. Okay, and all the time I have to clean up his mesh, which is not unique, right? So if we don't become strict, everybody will dump wherever they want, right? That's the nature of us. You know, we love to increase entropy, disorderness in life. Okay, it takes effort to be organized and clean up our waste, and that's the case. Environmental laws enable that. It gives a regulatory framework for the agencies to enforce laws that keeps our environment clean. And these laws evolve over time. It started with 1965 Solid Waste Disposal Act, and the last law was in 2018. Okay, so I'll go over some of those laws and what it means. These are a couple of quiz questions. So I'll tell you what are those important quiz questions. So understand the first one, 1965 Solid Waste Disposal Act. What it does, it before there was no act, so that means I can dump wherever I want, right? So that means your waste are being dumped into rivers, and now this river is catching fire. So what it does, it prevents you to dump waste into natural resource. It also enable people, it recommend people to reduce your waste so that you don't have to deal with and dumping somewhere else. So it's more about municipal waste, industrial waste, everything, so that they have a process to minimize it and not dump into rivers. It was not very effective because it doesn't have any power. The law didn't have any power. It's just recommendations, right? And the enforcement was missing. Who is going to enforce? 1965, municipality didn't have the power. I mean, who is the power to say that you are doing something wrong? There was no EPA there that time. So that's why the limitation was there. So EPA was created in 1970. Okay, 1970 to enforce these things. Not only that, there was issue about waste is being created 50 years ago, and who is going to take care of it? Imagine you buy properties, is already wasted by somebody, last owner. Who is going to pay for the cost? If somebody sold you that property, you are the one who is taking all the burden. That was not fair. So I mean, if you imagine the magnified level, big industry, they pollute it and they leave, they sell the land to somebody else, a city, and then the city has to bear the cost. So that's why this law was created. As you see, Resource Conservation Recovery Act. Actually, not my bad. It was more about getting the recovering the materials out of it. So instead of just minimizing the waste, it gives the framework to make the regulations, and also it says that why don't you recover as much resource possible before you throw that waste. So it was more about giving the regulations and minimizing the waste and by recovering some of them. And as you can see there, they don't really say about anything about waste here. They say resource. This is the first instance they give these indications that waste is not a waste. It's a resource you can take out of it. Okay, that's why all the wastewater treatment plants, all these things come here, because now wastewater treatment plants is a resource, because they can collect water out of it. But this law didn't give you any authority to go after the owner who actually did the damage. So there was no compensation given to the new owner. That person has nothing to do with the causing the mess. So that's why this law was created. It's called Resource Conservation Recovery Act. Hold on, where did that go? This one, 1980, Comprehensive Environmental Response Compensations and Liability. As you can see, compensation and liability. What it does, it it makes every owner who use that site liable, even though you are not the active owner right now. Not only that, it gives you a mechanism for compensation. Every time you drive a car, you pay some tax for the gasoline you pay for, and that goes to this fund. Okay, they are paying for cleaning up all the bad sites that people left over. Because normally, imagine there is a brownfield site or superfund site, which is very polluted site. That's the definition of superfund site, because it is so polluted that the existing owner cannot afford to clean it up. So it declares superfund. That means it enables the government to pay this money to clean up the site. So these are the mechanism behind it. And then 1984, there was a Hazardous Solid Waste Amendment Act. It basically enforced the industry to treat it waste before they dump it, because industry can pay for it. That way the landfills are not capable of handling so much waste. They want to minimize the number of landfills. That's why it regulates the amount of waste that can be sent by industry. In that Resource Conservation Recovery Act, they have to classify a waste, what type of waste, so that they can handle it. These are the symbols you can see many times when you drive a car. You see there are trucks going. They may have the symbols. This means what type of it. It enables the other people to understand what kind of risk they are getting into if this truck by chance cause accidents. And this is also the symbol you might see if you walk into any labs. The door has those symbols, because that also says what kind of chemicals is used inside the lab. That way you take the precaution. So most importantly, we are trying to avoid anything hazardous. This is a quiz question. There are 4 reasons why a substance can be hazardous. Number 1, it's ignitable, means it can catch fire automatically at certain temperatures. If the flash point is below 60 degrees Celsius, that means it can catch fire below 60 degrees Celsius, and that's basically above 60 degrees unnatural, right? Because you never have those high temperatures. So in normal condition, like below 60 degrees, that can happen. Even your cell phone can heat it to 60 degrees Celsius, right? Even 100 degrees, it can so hot sometimes. So that's why it's written, anything that catches fire within 60 degrees Celsius is hazardous. The second one is corrosive. Corrosive is related to pH. So they define any substance which pH less than 2 or greater than 12.5 is too corrosive, and that becomes hazardous. Do you know why the number, what's the pH of Coke that we drink? Coke or any kind of soda. I'll write it here. .5, okay, around that, or 3.1 to 3.5, and this is a log scale, by the way. Okay, so 2 to 3.5 is not 2 to 3 is 10 times more. Okay, and the reason it's a 12.5 is because if they make it 12, you're at home, if you have bleach, that pH is very high. Okay, so if that's the case, that means they have to declare the very usable product like bleach as hazardous. That means there will be regulations, so many things. So that's why bleach is right at the border. It is very corrosive. That's why you should not use it so much. You should not dump too much bleach into anywhere. It corrode everything. So that's why the pH range is 12.5. Anything between 2 to 12.5 is not hazardous by definitions. Okay. The third one, it has to be, if it is reactive, that means if it's unstable and it can explode, that makes it hazardous. For instance, all the gunpowder is hazardous because it's reactive. If you put a sodium, just a pure sodium in water, it explodes. That's why it's hazardous. Okay, that's react. The fourth one is toxic. It's very toxic. So that means if you inhale or you are exposed to that, it causes high reactions. So these are the four things. As you can see, the one thing that is hazardous but not mentioned here is medical waste. Okay, medical waste is not classified as hazardous, but is hazardous. It's handled very different way because it's related to disease. So every medical waste is hazardous, even though they are not one of them. They're treated as hazardous because of the reason. So this is basically one question where I'll give you a substance. I'll say this is the characteristic. You have to say whether it's hazardous or not. Okay. I discussed this one. So now that we discuss all that, let's have an example quiz questions. Which of the following laws account for hazardous chemical spill occurred in past? So think of anything happened in the past. What word in this, one of those has this word that related to things in past? Okay. So raise your hand if the answer is A. I'm not raising anything. Okay. Raise your hand if the answer is B. You got it right. Okay, because liability, that's past. Okay. All right, next question. Does Resource Conservation Recovery Act include liquid or gas hazardous waste? Because it says solid waste. I didn't really mention clearly, I skim over through it, so you can answer it based on what I spoke. But that's a good thing, you can clarify. So it's basically I'm asking is the Resource Conservation Recovery Act, RCRA, talk about solid waste. Does solid waste means also anything liquid or gas? Raise your hand if it is yes. Raise your hand if it is no. See that, I mean, I say solid is liquid or not, so it's intuitive, right? But think of this. If I give away bottles full of gasoline and say this is solid because it has a shape, right? It's maintained inside the shape. And give you that and say is this a solid waste or has not a liquid waste? You will treat as a solid waste. Solid waste means everything that has a shape. Okay, so even the liquid and gas inside a container is solid waste. Okay, that's a good thing, we discussed that. So answer is yes, include liquid or gas. The state of a substance or the phase of a substance is nothing to do with it determined as a solid waste, because whether gas or liquid, they are all inside a container. They are treated, by definition, they call solid waste because of that. Okay. All right, which one of these is not a characteristic delisted hazardous waste? Means I'm asking which is not hazardous. Which of these characteristic doesn't constitute them as hazardous material? Raise your hand if it is answer A. Raise your hand if it's answer B. A lot of them. Raise your hand if his answer is C. D. Okay, good. So we got 2 out of. Oh, you have a question? Yeah. So medical waste is hazardous, even though it doesn't have any of this characteristic. That's all I mean. Okay. For instance, glove. Think of somebody used glove after surgery. That is a medical waste, even though it doesn't have any of it. It doesn't catch fire. It's not corrosive. It's not reactive. It may not react. It is not. There's one thing missing. Corrosive, reactive, toxic. Oh, well, toxic is, but how it doesn't have anything that can really cause right away some toxicity. But it's just the precaution that there could be anything. So even that waste that gloves is used for a purpose which is nothing to do with any patients or infectious disease. It will be treated as hazardous waste, and they just burn it. Which one of the following pH is not considered corrosive in RCRA? One of them is corrosive. 2 of them is corrosive. 1 of them is not. Raise your hand if it is A, B, C. Okay, got it. So 12.5. 2 to 12.5 is not. Sweet. Now we'll get a very good grade in a quiz. Okay, because I can't ask any other question. It has to be some way related to this. Okay, so next 10 minutes, we are going to discuss about site characterization and remediation assessment. The reason is important now that you learn what is hazardous. What if somebody dump a hazardous material at a site? How do you know this site is dangerous to you or your family or anybody else? And when you know that one, what you or the agency or the government agency or the company can do it. You may be working in that company, you are going to help that landowner to clean up. So this is very important. The assessment is all about understanding the risk and minimizing the maximum risk first. So that's why assessment is one of the most important part of any remediation design. And many companies are there to pay for millions of dollars or take millions of dollars to do that assessment. Because if a big corporation buy land, they want to make sure that the site is clean. And so those assessment study can take months. So for instance, this example, this particular site, the few landowner or the homeowners, they live there on a golf course. They thought it's a beautiful place. Then they start getting sick. They realize they are living on a top of landfill. And the person who sold that golf course didn't say that it was built on a landfill, okay, or the old landfill. So how do you find those? What kind of way you can, if they would have taken some water below ground as a testing, or the company who did the assessment, they would have found that there are pollution in the soil. If they would have taken some gas emitted from the soil and measure it, they would have found those contaminants that every day these homeowners are inhaling. Okay, so these are the things company miss, and how do you know that? Okay, so this is just one example I'm going to give you how to do site assessment based on this one example. So think of there are two things. The very first left side, that's basically the gasoline. You buy from gasoline from a tank. This is the tank look like. Every gas station underneath, there's a big tank full of gasoline. That's made out of material that should not got damaged with time, but it does. Okay, it corrode. No, sometimes it happens. Proper maintenance is not taken. Then they will leak. All the oil or the gasoline will leak, get into groundwater. As you can see, there is a clear difference between the left and right side. Right side is a dry cleaner. Dry cleaner is basically using an organic solvent to clean your shirt. There is no water there. Okay, that's why it's called dry cleaning. Because those organic solvent evaporate. That means it doesn't stick with your materials, and you don't have to do a lot of things. So those solvents are has a unique properties. So who can tell what's the difference between, as soon as get to the groundwater, there is a clear difference. Can anybody says what's the difference when you see those in groundwater? They're both organic, but when they mix with groundwater, there's something happen. Yes? I mean, anything what you see that's exactly what's the answer. What do you see? Yeah, one stays at the top. Okay, another stays goes down. So if you spray a little bit of your oil, that cooking oil on water, stay on the top. Okay, that's normally most oils stick on the top, but very heavy organic solvents stick at the bottom. So it's called DNAPL, dense non-aqueous liquid. Okay, petroleum liquid. That's the DNAPL. Okay, dense non-aqueous means it's not water. Petroleum liquid. Okay, that's just the way to the remediation industry they call them, group them into DNA. So because it's dense, it's going to sink in water. It's going to start going down into groundwater. So if you one of them, you have to clean up. This one is easy to clean because you can just extract water by just pumping water. The other one is just going to sink, keep sinking towards the down. So you have to really clean so much area, whereas this one not. So if you are doing assessment studies, you got to dig a bigger hole there, all the way to bottom. So that can inform you what kind of hazardous waste material you deal with. So if you are remediation engineers and somebody asks you to go to that site, you got to have this information. You got to have an understanding of what kind of pollutant you expect and what's their properties, where do you expect to find them, because they are not visible. They are not there to introduce themselves to you. Most of the time you can't see them. Most of the time you can't smell them. Most of the time you can't feel them. That's why a lot of people it's too late for before they find about it. So your goal, but you have the power because you understand the chemistry of the pollutants. You can predict. You can think of what can happen. Then you can go to the right spot at the right time, find those pollutants. So this is the first thing how to do. Is imagine this is your house, and somebody says do an assessment study here. Your first thing is to do is what are the different risks around here. Risks means where the pollutant can live. So this is a river over here. As you can see, this is a river moving, and the ground river flow is this directions. And there is an underground storage tank here. There is a PCV storage area here, and there is a transformer. There are 3 sites. So these are the potential source where the solvent can leak. So if you are doing assessment study, you got to go there, take the soil samples there, so that you can define whether there is any kind of leakage happen in that sites or not. And then if you are trying to understand if the leakage happen and where it gone, because maybe they remove the transformer, there is no trace of transformer at that point, and anything on the solvent on the surface will evaporate. So that means there will be nothing on the soil on the top surface, but things will be down bottom. And not only that, if there is rainfall, they are all moving downward. They are washed up and going downward, and they maybe the groundwater will wash them up to certain directions. So knowing groundwater flow, you can also collect samples from the downstream, because that pollutant might have moved many far away from the site. In fact, you already know how to calculate that. You know retardation factor. You can use that equation to calculate how far it might have moved. So this assessment study is all about using that skill already you learned. So pre-assessment study, you in the desktop study, what they do is they look for all these source, all the different things. They brainstorm it. This is the site I have to go. This is the things I have to take. This is where I have to take. So this is something you brainstorm right inside your office. Then you go out to the field, dress up like hazmat suit, like you see over here, because you don't know whether you'll find any pollutants or not. You don't know what's the risk there, so you have to protect yourself. Take this hazmat and then you walk around, take samples, the location that you decided. A lot of times you have also in situ monitoring, like if you see that guy, what he's doing is he's using radar to understand the soil properties, how porous it is, where is the groundwater, how far it is from the surface. That way you can do the assessment. Then you do the marking like this, so that you can come back and do digging if you need it. So as I said, sampling means soil, water, air samples. If you know what kind of soil, what kind of pollutant it is, you can decide these things. For instance, if somebody spill a gasoline, and they say there is a spill there, and you went there after 1 month, you're not going to find anything in the soil or not in the water, because everything must have evaporated. So what you need to look for is air, but the air is, if it is not enclosed, it must have also become diluted. So you have to know where things should be, whether the pollutant will stick with it or not. So again, so these are the different steps. Once you determine that, you have to also understand all these other aspects of it. How far they will move, what's the exposure, who are going to be exposed to, how do you determine that? And based on that, it's basically based on if the pollutant is a volatile or the pollutant is sticky. You can see where they are. And we'll do those calculations in this class. So again, one of the other thing is where to take samples. Is it soil, water, or air? That's based on what's the chemical you are dealing with. So end of this class, you can watch a chemical and you can predict that. I'll give you some examples. Mostly we'll deal with organic pollutants. So that's also a quiz question. You kind of know those things, but I'll reiterate again. All right, so let's predict the fate or property of organic chemicals based on its structure. Means if you look at the organics, you can predict the structures. All right, so what we can do is we can take a 5-minute break because I've been talking for a while. So let's take a break for 5 minutes. Then we come back, we'll predict this. All right, so now how do we predict fate and property of organic chemicals if you see the structures? It's like, if you see somebody, you make a perception about it, but this is more realistic. You can't know about a person just by watching. That's very much biased thinking. But chemical, you can be very biased. You can see the structure, you can predict exactly what they're going to do. So these are the 3 things you can predict, and this is the formula. This is only thing you have to remember when you answer a quiz questions. The first thing is water solubility. How do you know if a contaminant is water soluble? Just count the number of carbon atoms, because carbons doesn't like to be in water. If you have too much carbon, it's hydrophobic. Hydrophobic means it's phobia to water. Hydro is water. If you have too much carbon, it doesn't like water. It stays. That's why oil stays at the top, because it has just too much carbon. Okay. If you have more oxygen, nitrogen, this kind of group, they are polar group. They make bond with water. Water has the polar group, polar solvent. So all you have to look for is decrease in number of carbon will increase the water solubility. Okay. And second, any kind of functional group means something that can react, that plus or minus ions, that will make it soluble, because that can that makes it polar. So any functional group with hydrogen bonding will bond with water. Water can bond with each other by hydrogen bonding. So we'll talk about functional group later. What kind of functional group? Then next thing is, how do you know an organic chemical is volatile or get into air? If the organic carbon, think of wax. Wax is like a candle, right? That doesn't evaporate by itself. Wax is organic. It's the same as gasoline. The difference between gasoline and the wax that you use is the number of carbon. Methane is volatile. It's always in atmosphere because it has 1 carbon. Ethane, 2 carbon. Ethanol, 2 carbon. Okay, so that's why they evaporate. Ethane can evaporate. Ethanol doesn't. That's why you can see ethane in a gas, but ethanol is a liquid. The reason is that functional group OH. Ethanol has a ethane, the same carbons, but it has a OH group. OH it can form hydrogen bonding. So that's why they can bond with each other ethanol atom and they become liquid. Okay. So this is basically intuitive. All you have to think of is the same way. If you have functional group, they can bind somewhere, they bind with each other. That means it's difficult for them to escape into air. So that's why ethanol is less volatile than ethane itself. Methanol is a liquid or less volatile than methane itself because of that functional group that cause hydrogen bonding. So how do you know if an organic chemical will stick with soil? Well, you know that if you remember retardation factor, or if you remember KD, that's the basically how efficient they are sticking with soil, is FOC times KOC. So KOC is basically affinity of that pollutants to organic carbon. You just learned that organic the carbon doesn't like in water, right? So any organic carbon can also bind with another organic carbon by van der Waals or other interactions. So that's why any organic chemicals with lots of carbon in it are so heavy and so doesn't like in water that they will stick anything else. And when they find soil, they stick with that because they don't want to be in water. Okay. So anytime you see increased number of carbon, that means it's going to stick with soil a lot more. So these are all intuitive, right? So now let's answer some quiz question. You will see. So this is also example. Benzene. That's like a ring. Each one is 1 carbon, each corner. That's the structure. So there are 6 carbon there. But the comparison between benzene and phenol, the only difference is we have OH here. This OH. This OH can cause hydrogen bonding because there are electronegative difference between O and hydrogen. They pull the electron cloud, so oxygen pull it towards it. So oxygen is partially negative, hydrogen is partially positive. That means they can interact with another OH. And that OH exists in water because water is HOH. So that's why they interact with hydrogen bonding. They interact with each other by hydrogen bonding. So if I ask you between benzene and phenol, which one is volatile? More volatile. What you will say? Volatile means they don't have anything to hold to. They will escape. So you remember from the previous question, having a functional group that can cause hydrogen bonding make them less volatile. So that means this has OH, phenol has OH, so this is less volatile. And because it has OH, it can cause hydrogen bonding. It's also more soluble in water, okay, than benzene. Okay. Same thing if I ask you between phenanthrene and this, the last one. You can see which is more volatile based on this. Okay, that's the Henry constant. The Henry constant low means it's a very small number. All that. So again, we talk about this thing. I'm not going to go details. Let's say the quiz questions. If an oil spill contains the following chemicals, which one of them would be present at high concentration in groundwater? So in other words, I'm asking which of these 2 chemicals will have more solubility in water? Raise your hand if it is A. Raise your hand if it is B. Okay, so let's think of it. What's the difference between these 2? First one, exactly same number of carbon, so you can't use the carbon arguments. Okay, the only difference is one has OH, another doesn't have OH. So what OH does? It causes hydrogen bonding. Okay, so if you think of what hydrogen bonding is, this is water. This is relatively plus charge, this is relatively negative charge. That's why it's called polar, because oxygen is very highly electronegative that pull that shear cloud towards it. That makes it more negative. So when there is a, let's say any OH group from, imagine this is the OH group and then you have this carbon structure. This negative will interact with this positive will interact with this. So this is called hydrogen bond. They will also interact with the OH bond from each other. So that makes it easily soluble in water. That also makes it also interact with each other, not escape into atmosphere. So the answer is this, because it has the functional group that makes it water soluble. Now I ask you another question, but now you check what's missing here. If an oil spill contains the following chemical, which one of them would be present at higher concentration in groundwater? So first of all, carbon, number of carbon is a factor as well as the functional group. So if you see between these 2, A and B, okay, why am I answering the question? Raise your hand if it is A. Raise your hand if it is B. Raise your hand if it is C. Okay, so the answer is actually C. I'll tell you why. Now between A and B, both have functional group. Okay, the same functional group. That means they are trying to bind with water, but there is one thing difference between them 2. The number of carbon in A is much more than number of carbon in B. You just learned that if you have too much carbon, it doesn't like water. So that means that will like less water than the other one. Okay, so this smoke going to dissolve. All right, so that now you know how to answer quiz questions on these slides. Okay, so what we're going to do is now we are going to calculate how long this will go. Okay, how long the pollutants will leave. And that's basically you have already done. You know, you have solved the groundwater question in midterms. That's basically these questions. You know the pollutants, you know the aquifer properties, you know the pollutant properties. You are going to basically calculate the distance the pollutant will migrate or the velocity of pollutants using retardation factor. So that means you have to know the concept of retardation factor, which is velocity of contaminant divided by velocity of water, which is 1 plus ball density of soil times fraction of organic carbon times KOC divided by porosity. And velocity of water is basically Darcy's velocity divided by porosity. And Darcy's velocity, you know this one, Q over area is K is hydraulic conductivity. So use this equation to solve many questions. This is exactly the same thing. The only difference here you might not know is KOC. Sometimes KOC is basically what's the affinity of the pollutants with organic carbon. But now organic carbon could be anything. You take, let's say, beer, that has organic carbon. You take honey, that's also organic carbon. You take many types of liquid, each one is different types of organic carbon. So that means if your organic carbon is varying, how do you know which organic carbon affinity, which to what specific? So that's why what scientists did is they say, okay, let's standardize everything. All you are going to see is what's the affinity of that pollutants to one type of organic carbon. That's called octanol. Okay, so what they do is they mix the pollutant, what is already in water, mixed with octanol, and see how much of those pollutants get into the octanol. Because if more is going to go to the octanol, which is a solvent, with 8 carbon, basically 8 carbon and OH. So what it means that people can determine, which is called KOW, octanol water coefficient. So octanol water. So basically you mix pollutants in a mixture of 50% octanol, 50% water, and you see what percentage stays in octanol. If more goes to octanol, that means it's more hydrophobic. So what it does, it basically a constant. If you know KOW, which is easy to measure, you multiply that with some constant value that's determined experimentally, you determine KOC. And then you put back over there, then you determine all that. So again, the homework questions, what you get in this class is a combination of groundwater because of this reason, because you'll know chemicals and you'll have to determine these properties and then use it. So I'm not going to solve it because this is exactly what you did in homework on midterms. So try to understand that and do it. So do it by yourself. You learn that how to do it, but this is just I put it there. I'm going to put the solution here after the class. I don't want to repeat it here. When I upload the annotated slide, it has the solutions. Now the last thing, you found out what chemical is there. You already predict where this is going to go. And imagine that most of the time what we deal with is the groundwater pollution, because once it goes to air, it's all there. Can't control it. It doesn't have any boundary. So what we are going to control mostly is the soil pollutions as well as groundwater pollutions. soil pollution doesn't hurt a lot of people because you can cap it. You can cap it, you are not exposed to that soil, you are okay, right? That stays there as long as you are not digging that soil. Groundwater will hurt people because that groundwater is not staying there, it's moving far away, and somebody in the downstream is going to drink it. In fact, that's what happened most of the cases. Many places the groundwater pollution happens in upstream, and now we are drinking it. We are drinking that toxin. So it's very important to clean groundwater, and many of the remediation technologies around the cleanup of groundwater. So in the very beginning, I said that what people do is ex situ treatment, where they takes all the pollutants away, treat it, and then it put it back. So this is one of the technology that was used extensively in 1980s, which is pump and treat. So what do? Is they create this capture zone that you learn in the groundwater class, how to create this capture zone. They pump all that water. So that capture zone is relevant right now here, because you are basically taking all the flume, and what you do is you hold on. I'm sorry, this I've been talking all along, and then the microphone was not working. That's my mistake. We'll see how the video is, but if it is worse, then I have to delete you guys for the last year video. Okay, you guys okay, but I'm feel sorry for the people who are on the Zoom. I didn't see the microphone was not working. Now it's working. All right, so when you see this one, contaminant removal, the pump and treat method basically pump all of them and treat them using activated carbon. So what people do is, like, imagine your Brita filters or that big filter. You take that filters, fill of carbon, activated carbon, and then you pump that water through it, and you extract all of them. The only concept you have to know is that KD. Okay, KD is basically how much pollutant can stick with carbon. So concentration in carbon, which is concentration in carbon, then concentration of water, contaminant in water. You know this concept already. Basically, if you mix a polluted water in with a solid, certain amount of polluted water will get into the solid. An amount adsorbed, which is Q, is proportional to the amount of pollutant remain in the water, C. So that proportionality is KD. Okay, so this is a linear equations, but in most of the time, this is not a linear. This is non-linear equations. So that means a contaminant concentration in carbon is equal to some coefficient concentration times this is Freundlich they call Freundlich isotherm is because this whole process is taken at the same temperature. If you do at different temperature, the K value, constant value will change. So what it means that you can predict the concentration in water if you know the K value. Okay. So Q is the concentration adsorbed on carbon. Concentration of pollutant adsorbed on carbon. This is concentration remain in water after adsorption. And your goal is that C to be as small as possible, right? Because you are treating those in that activated carbon tank, and you are going to remove them. So this is what they do. If you see in line, this is what it works. These are the different tanks filled with activated carbon. They fill with them, and then they pump contaminated water in one end. It pass through one activated tank, and then again it feed to the next activated tank. Then it goes on like that. The reason they use 4 in series or more in series is because what if one failed? Is still protected. And if one fell, that means they can remove it while they are still operating the other ones. That way they can replace it whenever they need in series without stopping the operations. So that's why they are in series. So these are the definition. A lot of times people use hydraulic retention time. This is the same empty bed contact time, means how long the polluted water will stay inside the system is 5 to 20 minutes, which is basically volume of the tank divided by flow rate. Okay, volume of tank, which is empty bed. This is the flow rate. That means you have basically maximum 5 to 10 minutes for the pollutants to be absorbed into the activated carbons. The treatment depends on surface area or property of activated carbon. It's called granular activated carbon. GSC means granular activated carbon, the size of the activated carbons. If you have high surface area, that means absorption process is a surface active process. That means it will stick on the surface. So it will work if you have high surface area, more absorption. And some high quality activated carbon will remove more pollutants. So it also depends on quality of adsorbent. It also depends on contaminant type. You just learned that if you have more number of carbon, it will stick with more carbon. Okay, so that means if a pollutant is more water soluble, it's not very good for this treatment. You need something which has more carbon so that you can stick with activated carbon. It also depends on water chemistry because it interferes with the adsorption itself. So a lot of times, if you want to calculate all these things, you need to know all these other factors. These are the design. How long it will be treated before you have to replace that tank. What is the empty bed contact time if you want to calculate? So formula is given. What's the removal rate? How quickly you have to replace the activated tank? So that's why this is one calculation you have to do, or example you have to learn in this class. So now a little bit talk about activated carbon. What is activated carbon? You take any carbon, let's say you take this wood, break into small pieces, you can create activated carbon. What you do is you burn that wood inside a closed container without any oxygen. If you burn with oxygen, let's say it catches fire, what you see is flame going up, and then what is remaining is just the ash. All carbon become carbon dioxide. So if you replace entire this room with no oxygen and you really heat that up, it will catch fire, but it's burning without oxygen. So that means this carbon will not change to carbon dioxide. This carbon will just, all the other things, the oxygen, other things will replace and break it away. This carbon bond will not break. So what you remain is like graphite. If you remember the pencil tips, that's the graphite. That's look like that hollow honeycomb structures. So graphite means it's just a carbon, nothing else. Activated carbon means it's just a graphite like shape, and what you got is just basically a carbon, just like charcoal, but it's not activated because it has so much pores that is blocked with oil and stuff like that. So what people do is they apply steam. The high steam, because steam has high temperatures, the water compared to water, they pass this high hot steam through it, it open up the pore. When it open up the pore, it has nanopore that will attract lots, increase the surface area. So basically you take a charcoal, activate it. Activate means applying the steam or the process to open up the pores. So that's called activated carbon. If you see Brita filter, this is how it is produced. Okay. Now that you know the concept and you know adsorption, you can solve this question. So let's read the question. I'll tell you how to solve it. That way you know how to do the example questions. This is the I mean, this class is the last class with any quantitative questions. So that means the next homework is based on this class. Okay. So these two questions are related to your next homework questions. That's all you have to learn. So this is the last. I mean, there is a quantitative question on air quality, but that's basically putting equation on getting the answers. All right. So removal of a contaminant by activated carbon is expressed by friendly isotherm in the form of this. So what it means is Q equal to 0.1 C to the power 0.3. This C is concentration of organic in equilibrium with bulk solution. What it means that what's the remaining pollutant in water after absorption occurs. Okay, so this is concentration of pollutants in water after adsorption, and this is concentration of pollutant adsorbed on granular activated carbons. That tell how much contaminant is in activated carbons. So that means if you can use this equation, if you know what is the effluent water quality, what is the concentration of pollutants after adsorption, then you can predict how much pollutants is in the activated carbon. If you know what's the concentration of pollutant in activated carbon, you can also calculate what is the amount of activated carbon you need to remove all the pollutants, because you know how much pollutants are coming. So that's the whole thing about this problem. It says how much activated carbon should be added to treat aqueous solution of concentration 0.45 moles per liter to reduce its concentration to achieve treatment goal of 99%. Okay, so I'll write what is given here. So this is your treatment goal. That means this is how much you remove. Okay, removal. This is the volume of water you are treating, or the Q. Q is 100 gallon per day. This is your concentration initial. That means how much pollutants is coming in water. And the question is how much activated carbon is needed. How much activated carbon you need. If you know what is Q is concentration of pollutants in activated carbon. Q is basically mass of pollutants absorbed mass of activated carbon, because if you see the concentration is mole per gram of activated carbon. And what I do is I ask you this. Okay, so that's the thing. So you got to put this value over there and get the answers. So let's write the equations. Q equal to 0.1 C to the power 0.3. Mass of pollutants. So if I write P, that's the pollutants absorbed by mass of activated carbon. This is concentration. So basically you have to solve for to do that, you have to also calculate other thing. You don't know what is C, you don't know what is M absorbed, but everything other information given to you actually gave you that information. So let's say, what is the concentration of pollutant after adsorption? It's give you already that 99% is removed. And it give you initial concentration 0.45. So that means 99% remove it, you got the answers for C. So C equal to 100% minus 99%. So it's 0.99. times whatever the initial amount coming in. That means only 1% is a 0.01 times C in is 0.5 mole per liter. So you know the C now. And what is M absorbed? That's something. How much pollutant is absorbed, you can also predict, because everything that is not in water is all gone to the activated carbon. So if you know what is the initial concentration, what is the final, the difference is what goes to activated carbon. And you know the volume, so that means concentration times volume is the mass. So basically volume of water treated times C in minus C. Volume is 1000 gallon per day. C in is 0.45 minus 0.0045 moles per liter. Again, there you have to change gallon to liter, because the concentration is moles per liter and the volume is in gallon. So you have to change 1 gallon 3. I forgot 875 probably. Then you basically get how many moles per day. Means if you operate the system for 1 day, how much moles of pollutant absorbed per day. Okay. So now if you put those values, then MASC, amount of activated carbon, is basically in gram. Okay, because that's the answer, is that concentration is given in gram. Is M absorbed which will be basically more per day. Okay. By 0.1, you don't have to take care of the unit here, because the constant, that 0.1 has that unit to cancel out everything. Okay, so whatever it is, it's already accounting for that unit. So you put, as long as you put this value as the unit, it says moles per liter, you should get the answer, the other one, that. So whatever number you will get in gram. Yes. Oh, okay. That's because I learned to how to make mistake all the time. Thank you. 0.3. I don't know why. I like 13 numbers. Maybe that's why. My wife's birthday is on 13th. That's maybe the reason. I'm just trying to justify something which is unjustifiable. Okay, so that's the answer. Okay, that's, you learned the questions. And second is, what would be the height of activated carbon tank if the area is certain things? So basically, you know the mass, you are going to pack in something. Okay, so it says what's the height. You know the bulk density. Bulk density is, it's not right. I'm going to explain in 1 minute, then we'll go. You know the mass of activated carbon has to pack, right? And what is the volume of activated carbon? That's what is mass of activated carbon. Mass per volume is density, right? Bulk density. So if bulk density is given, mass per volume is bulk density, packing density. So that means if you want to calculate volume, it will be mass per bulk density. So you know the volume of activated carbon, right? And then you know the area of the tubes. If you divide volume of activated carbon by area, you'll get the height. Okay. This is packing density. Bulk density same as called packing density. So that's basically it now. So you already know those numbers, so you can get the answers. All right, so we are able to finish this class even though we have 15-25 minutes of delays. And I also had in between, maybe in the recording, didn't record everything well because the microphone was off. So if you are one of them, just please watch the last year video. I'll post the things. It's the same thing. Okay. All right, see you next Monday. Homework is released, so please work on the homework.